All right. So Gaspard is a master student in the lab, and he's going to talk about reducing the RF inhomogeneities for ultra-high-field MRI applications.
All right, so hi everybody. So as Julien said, I will talk about the RF inhomogeneities and their reduction for ultra-high-field applications. So first, is everything working like the slide? Yeah. I guess. So first, I will try to explain why do RF inhomogeneities exist in MRI, especially at ultra-high field. So first, what is the RF field in MRI? So the RF field is the one that tips the spin in the transverse plane. So that's what is going to generate a signal that we will measure to get the images that we have in MRI. So this RF field is a major component of the MRI process. It can be divided in two subfields, the B1 plus field, which is like circularly polarized in one direction, and the B1 minus field, which is circularly polarized in the opposite direction. Here, when I will talk about the B1 or RF field, I will mainly focus about the B1 plus component that tips the spin. This is the one that tips the spin because this is the one that is circularly polarized in the same direction as the spins. So yeah, maybe I will do some shortcuts and just call it B1. So the B1 minus component is more related to the signal that is received during MRI image acquisition. And in order to tip the spin efficiently and to be able to record a signal, the RF field frequency must correspond to the Larmor frequency of the spins, which is given by gamma B naught, where gamma is the gyromagnetic ratio of the spins and B naught is the main static field strength, so the strength of the scanner. All right. So the RF wavelength will decrease when B naught increases because, like as we saw, the RF wavelength is related to B naught. The RF frequency is related to B naught. So when the frequency increases, the wavelength decreases. It will decrease following deceleration, where the permittivity, the electric permittivity will play an important role. And with the main tissue characteristic for a human body, we have a wavelength that is around 12 centimeters at 70. So 70 is considered to be as ultra-high field MRI. So 12 centimeters becomes smaller than most of the body regions we want to image. So it will become harder to have an homogeneous B1 field at such fields. So the RF field become inhomogeneous in the human body, as we can see here on these images acquired by Matthias Deringer and his team in 2014. So these images are really great because we can see that at 1.5 T, we don't have to really care about this wavelength effect because we have some pretty homogeneous B1 field across the head of a patient. But we can see that at 3T, it becomes to be a little bit inhomogeneous, and at 7T, it's completely inhomogeneous, and that's where we want to correct it. So the RF interferences are also, so RF interferences will also be observed when several transmit elements are used. This means that like there will be constructive or destructive interferences that will amplify this inhomogeneity, and that will be also even stronger at high fields. So why do we need to reduce these RF inhomogeneities? That's because the measured signal in MRI depends on the flip angle, because like the flip angle will be the angle that we use to tip the magnetization, and it will be higher when it's in the transverse plane, so at the 90-degree flip angle. So the flip angle is scaling with the B1 plus field. As we can see here, it's the integration of the B1 plus field across time times the gyromagnetic ratio. And an inhomogeneous RF field will thus induce an inhomogeneous image intensity because the signal will be inhomogeneous across the image. So as we can see here it's just some simulation that were done in 2005. So we can see that with one coil at a low frequency, we have some like quite homogeneous profile around a phantom. But when we go to a higher frequency, we have this kind of wavelength effect where we have some positive and negative poles. And we can also see that with two coils, like at slow frequency, we don't have many like interference effects, but at higher frequency, the interferences are becoming like a little bit more visible, a lot more visible. And so that can be a problem in our images because we will have like drops of intensities at some positions. So that's what we can see here in like an abdominal image acquired in 2005, where we can see in the middle that there is a dropout of intensity that is due to RF interferences. So that can become a real problem when trying to diagnostic some diseases that are located in this area. So another thing to take into account, and that will be really important for what we will see next, is that the RF distribution is different for every patient. And also it will depend on the call setup, the position of the patient in the call setup. So yeah, every patient will have a different effect on the RF field. All right, so we have seen previously some B1 field maps. So now I will briefly show you some methods that can be used to map the RF field. So why do we need to map it? It's do you hear me? Like,
yeah, I think the internet. Yeah, there was some like glitch.
Okay, but was it
Can you
working?
reshare? We don't see your slides, so maybe you need to reshare your slides.
That's what I was saying so far. Did you hear it?
It dropped after you showed your slide. Yeah, I kind of lost you about there.
Yeah. Okay, so okay, I'm gonna start.
Maybe yeah.
Did you saw that?
Yes, we saw that. So maybe you can start from there. Yeah.
Okay. So yeah, okay. So the repartition of the B1 thing will be useful when we will try to homogenize it, because we will have to compensate for the different inhomogeneities that we can observe. So far, many B1 methods, B1 mapping methods have been developed. They can all be classified between like magnitude-based method or phase-based methods. I will come back to what that means later. And so far, no universal gold standard method has been developed to map the B1 fields in the body. So like all the methods that we can find are a trade-off between the time required to acquire the maps, the accuracy of the flip angle or the B1 field, which are related, and the patient safety, because mapping the B1 field will require to have some RF pulse in the patient, and that can be a SAR concern. So B1 maps can also be used to correct for like some various measurements that can be done. For example, the T1 maps. When we do some T1 maps, the values that we find for T1 for different tissues will depend on the B1 values. So having different B1 values across the field of view will induce some error in the T1 measurements, and knowing the real B1 values will allow us to recover the true B1 values. All right, okay. All right, so I will start by explaining how work some B1 mapping methods. I will start with magnitude-based methods. So the first one is the most simple and straightforward. It's the double angle method, or GAM. And it consists of two excitation pulses that will be used with different nominal flip angle. So we will try to flip the spins by two different flip angle. Usually we will use a second flip angle that is twice the first one. And that will give us, after some derivation of the block equations, that will give us an equation that allows us to recover the true value of the flip angle with the ratio of the two signals that will be measured. So we will acquire two images with two different flip angles, and the ratio between these images will allow us to recover the flip angle at every point of the image. So these methods require like a total the T1 relaxation. So it's pretty long because the repetition time will have to be higher than 5 T1. So it's a very slow method, and the whole brain mapping is estimated to be like around 20 minutes. But fortunately, some improvement can be done by, for example, using compensation pulses. That's what we can see here with that delta 1, 2, or catalyzed pulses that will just like make the relaxation go back to like an initial state where we will just be able to do another repetition faster without having to wait for the 5T1. Another method is the actual flip angle imaging. It's pretty close to the one we just saw, but here we will have two nominal flip angle that are the same, and what is going to change between the two acquisition is the TR. So we will have two interleaved TR, TR1 and TR2. And the flip angle will correspond to this this equation where we have like the intensity of the two signals of the two images at every point, and the ratio between the two TRs. So here, what is important is that it will work better if TR1 and TR2 are much smaller than T1. So that's really interesting because it allows us for short TRs. So the mapping will be fast, like a whole brain coverage will be done in around 3 minutes. And it has a low sensitivity to motion because the mapping will be really fast. So it can be useful for example, in moving regions such as cardiac imaging. This solution is also insensitive to T1, T2, and T2 star because of the small TRs that we are using. The spin density and the call reception profile will remain the same between the two acquired images, so it will also be insensitive to these things. So that's a pretty interesting method compared to the DIM. Another method is still a magnitude-based method. I will go through it quite fast. So it's using EPI. So two EPI redots are used for spin echo and a stimulated echo. We can have the flip angle here by this formula where TM is the time between the second pulse at 2 alpha and the third pulse at alpha. And what is interesting here is that it is a fast method, obviously, because like we are using EPI, so EPI will read every line of the K-space in one pulse. But the problem is that EPI is very sensitive to delta B naught because it will have a longer reading time, so it will let time to have phase shifts due to delta B naught inhomogeneities. And so it is not well suited for imaging regions with high delta B naught, for example, the spinal cord. And I will explain why it matters later. All right, so the last method that I want to show you is a phase-based method. So it's based on the Bloch-Sigurd shift, which is a spin resonance frequency shift that is induced when we apply off-resonance pulses to the subject. And this Bloch-Sigurd shift is related to the square of B1. So that's what is going to help us to recover the B1 value. So the RF information here will be in the phase of the signal, and it will be recovered using that formula where here we have the phase induced by the Bloch-Sigurd shifts. So we will just take two images, one with these off-resonance pulses and one without them. And the difference between these images will allow us to find that shift and to recover B1. That's a very fast mapping method because the whole brain can be covered in 25 seconds. And the B1 values that we can find with that method are really close to what can be found with DAM, so the double angle method. Here we can see the different B1 values, the B1 maps. So we can see also that the Bloch-Sigurd method won't be dependent on the TR because we approximately have the same values with a TR of 70 milliseconds and a TR of 2 seconds. So that's a really interesting method. The only problem is that applying off-resonance pulses might make a higher SAR. So SAR is the specific absorption rate. And when we have a radio frequency field in the body, there is some energy deposition in the body that is measured using the SAR. And so it can be dangerous for the patient at ultra-high field because the SAR becomes more important at ultra-high field. All right, so how to choose a B1 mapping method. So I just show some examples, but we could see that there are some differences between every method, and every method has its advantages and drawbacks. So when we are choosing a mapping method, the first thing we have to consider is the region to image. As I said, the spinal cord, for example, has a high B-naught inhomogeneity. So a method with low sensitivity to these inhomogeneities will be useful. The available time should also be taken into account, especially for clinical application where we have a patient in the scanner and we want to scan it fast. And the patient safety is also to take into account, for example, with the block Siegert method, because SAR can become a problem at high field. All right, so now I will talk about the methods that we can use to homogenize B1 and to get rid of the B1 related artifacts in the images. So some pretty simple method that has been tried at first are the post-processing of the images. So for example, here we have an example where we don't even need the B1 maps. So that's what is really interesting with that method. We just use some image processing, like some filtering, some segmentations, to have an idea of how the B1 field inhomogeneity is in the image. And then we can just correct the initial image and get a more homogeneous one. So that works well. We can see that this image is more homogeneous than this one. And we have also different methods that are based on the B1 maps that we acquired. So here we have the uncorrected image. Here we have the corrected image. And here we have the transmit B1 map and the coil sensitivity map. And we can see that using these maps to correct the image can yield a better visualization, especially in the areas that are here on where the gray and what matter are difficult to segment. And so the main, the advantages of this method are they can be performed offline, so we don't care about the time that they take, and we don't have to have the patient in the scanner during these methods. But the problem is that they won't improve the SNR and contrast of the images because they just use the information that was already there, and when we acquired the images, the B1 field wasn't homogeneous. We are just trying to correct it after. So the flip angle and the signal wasn't homogeneous. All right, so another method that can be used to correct for B1 inhomogeneities is the pulse design. So many pulses can be designed. We don't have to always use like some Gaussian pulses to excite or sync pulses to excite the spins. We can use a specifically designed RF pulses that are designed for a purpose. So here I will just present the fast KZ or spark pulse because it has become a widely used method for B1 inhomogeneity correction. It's composed of 5 direct functions in the excitation K-space. So the excitation K-space is like it's not exactly the K-space where we will measure the different images where we acquire the signal, but it's an excitation space where we will deposit the energy that will flip the angle. And so by depositing the energy at specific points in that K-space, we can have a Gaussian-like correction of the B1 field, and play this Gaussian-like profile will be really useful when we are playing with volume coils, because the volume coils will have like the opposite, like we have a central brightening that is almost Gaussian, as we saw earlier. So using this type of pulses can correct for these inhomogeneities. But also the energy deposition can be reduced because we are just depositing energy at a specific location. So it can allow for a star that will be lower than using like sync pulses or adiabatic pulses. But one major drawback of this method is that they cannot be adapted for any inhomogeneity pattern. We will always have to stick with a Gaussian-shaped correction, but we can play like on the shape and the curve of this Gaussian by playing with the values that we can see here. All right, so here are some examples of the improvement that can be pulse design can yield. So we can see here, like with a basic sync pulse, that we have a very important brightening in the middle of the brain. But with Spock pulses, we are able to see the differences between gray and white matter. And yeah, we can see that when we take the difference between these two images, the central part is where we have the most difference. So we managed to get rid of that central brightening. So that's an interesting feature. So now we'll talk about the RF-shimming. So the RF-shimming is a method that is based on the use of parallel transmit array. So we will have different transmit elements around the patient. And each transmit element will have its own complex shim weights. So one magnitude and one phase per transmit element. And the shim weights that we will use are determined by an optimization. So that can be performed with MATLAB or any optimization software. And so just let me show you an example. So here I have magnitude and phase maps that were provided by Sam Murad Deniz from New York University in one of his papers. And so these maps, I played with them. So on MATLAB, here is just the excitation that we got if we have only one phase and one magnitude, so no phase, and one magnitude on all the channels. And so we can see that we will have this B1 profile that is quite inhomogeneous. And by applying magnitudes and phase to each one of these 8 channels, we can have something that is much more homogeneous. So here we have a B1 field that is much more homogeneous than here. And we can see here that the COV, the coefficient of variation, which is the standard deviation over the mean, is decreased from 0.51 to 0.14. So that's a really interesting result. And here, during that optimization, that's what I wanted to do. I just wanted to minimize the COV. So here are some examples of RF-shimming in vivo applications. So here, for example, it's in the hip where we wanted to be able to visualize this circle here. We can see that without shimming, we have that drop of intensity, and with the RF-shimming, it's much more better. But we can also observe that in a large ROE, we have still some very inhomogeneous field. We can observe the same here with the prostate imaging. Without shimming, the prostate is very shady in the middle, and it's almost not visualizable here. But with shimming, it becomes more clear, especially with GRE sequences, but also with turbospinico. So it's a pretty interesting feature. And here we have the last example with the lumbar spine, where we can see, especially here on the top, that we have a much more homogeneous spine with the RF shimming than with that. So what is interesting also to observe is that we can only shim over small ROE with that method. So the region of interest must remain quite small. And we can also conclude that the RF shimming is important for diagnostic efficiency, because it's much more easier to diagnose when we have something like this than like this. All right, so the RF shimming is interesting because the optimization may aim for different objectives. So, for example, I show you that we can reduce the coefficient of variation. We can also aim for a certain flip angle over one region of interest, and we can also try to reduce the energy deposition. It's easy to implement with tools like MATLAB or Python, because they are optimization libraries that can be directly used to do our calculations. The homogenization is improved compared to a single channel excitation, as we saw just before. The main problem is that it requires one channel per transmit element. It requires the B1 maps for every transmit element, phase and magnitude. If we want to homogenize over a large region of interest, we'll have to have a higher number of elements. And the optimization is also constrained by the SAR, the specific absorption rate, especially at high field, where the SAR becomes more important. So one thing that has been developed in the last decade to overcome these obstacles is the full multi-channel transmits. So it's kind of an improved RF-shimming method where each takes element, so each transmit element has its own tailored RF pulse. So for example, we saw the Spock pulses earlier. So here we will be able to use some different Spock pulses or different other pulses on different channels. So they don't have the same RF pulse. The phase and magnitude of each channel can be time dependent, so they can vary across time. So that's an interesting feature. And so this will give us additional degrees of freedom. And so we will have a better homogeneity. So for example, here we have the one pulse, so the same RF pulse everywhere with the same magnitude and phase. And here we have the full multi-channel transmit. So we can see that the results are even better than with RF shimming. We can aim for a lower SAR because of the use of tailored RF pulses. We can have shorter pulses that will allow us for reduced scan time. And we can have a better spatial resolution also due to the use of tailored RF pulses. So the main problem with the full multi-channel transmit is that it's complex and it's expensive to have this additional equipment. For example, we will have to have one transmit amplifier for each channel. And the optimization process is much more complicated than with RF shimming, where we just had to look for one phase and one magnitude for each channel. Here we will have also to tailor the pulses, so that can require a long time. All right, so here is just a small comparison to see what changes between the single channel transmit, the RF shimming, and the full multi-channel transmit. So basically, that's just a summary of what I went through. And here we can observe the results. So here is a single channel transmit, here is an RF shimming, and here is a full multi-channel transmit using free Spock pulses. So we can see that the homogenization is much better. It's at 70, by the way. So the main obstacles when we are trying to do this RF shimming and multi-transmit method is the SAR at first. So as I said, the SAR is problematic because it will cause heating of the human tissues. So we'll have to be really careful about it. It's the amount of RF power absorbed by the tissue, and it scales with B0 square. So for example, the SAR will be 5 times higher at 70 compared to 3T. So that becomes a really big concern and a constraint. So we also have to look for local SAR hotspots. As we can see here, like the SAR is not the same across the whole body. We can have hotspots, especially when we have RF interferences that can be additive. And when we are designing our pulses, both global and local SAR has to be taken into account. So that can become a problem because we don't have the possibility to access some values in local regions. And we can see here that some regions will be very highly heated. So the pulses with a high peak RF pulse will have to be lengthened. So the scan time will be longer. So that can be a problem in clinical application. Yeah, so the PTX right now is used at 3T in clinical application, but not at 70 because of these concerns. And we don't know how it's investigated, but actually right now it's really hard to go under the legal limits with 70 applications. And another problem is that it's impossible to directly measure the SAR into the patients. So most of the time, the optimization with SAR constraints is done using simulations. And these simulations are not patient-specific. So we'll have to use safety factors for modeling the errors and the inter-subject variability because everybody is different. So these safety factors will make it even harder to go below the SAR limits. And another obstacle, which is a little bit related, is the scanning time, because the scanning time is limited during clinical applications. So doing the B1 mapping, the optimization of the sim weight, the pulse design with the SAR limitations, it's an additional scanning time that can be up to 15 minutes right now in 70 applications. So one of the main research interests right now is it's directed toward the time-saving methods. So I will present some of them here. So the first one is the use of virtual observation points. So it has become like very widely used. I think every study that I saw that were performing PTX optimization was using VOPs. So it's used to for the local SAR constraint optimization. So as we saw, the local hotspots may be taken into account during the optimization. So all the voxels that will have similar SAR matrices, so that will have similar sensitivities to the heating due to the electric field, will be gathered into clusters. And each clusters will have a new matrix called a virtual observation point. So this matrix will be the relation between the voxels in the patient and the heating, like the energy deposition. And so during the optimization, we'll just compute one SAR value per VOP instead of computing one SAR value for each voxel. So it can become up to 13,000 times faster than computing the optimization for all voxels. So that's a really, really important point. So that's why it's widely used. And it will also overestimate the SAR because we can't risk to have an estimation that will be lower, so we have to overestimate. And to have a small overestimation will require to have a higher number of VOP. So a higher number of VOP will make the optimization time longer. So it's a trade-off between overestimation and number of VOP. And the problem with the overestimation is that it will be more constrained by the SAR if it's higher. So with the time saved using the VOP, we can, it's the only thing that allows us to keep the patient in the scanner when we are optimizing the pulse for full transmit parallel imaging, parallel transmit. So that's a very interesting point. And the other one that other point that is investigated is like the use of calibration-free methods. So the universal pulses are one of them. So calibration-free method it means that it doesn't require to do some B1 mapping, some optimization, because the pulses are already stored in the scanner. So here with the universal pulses, we have non-selective pulses that are designed based on B0 and B1 maps for like a data set of patients. And so that yields a very, very promising results, as we can see here, because with these universal pulses, that doesn't require additional scanning time. We can have like a flip angle that is much more homogeneous than with RF-shimming or with CP mode. And RF-shimming is patient-specific. So with a method that is not patient-specific because it's just based on a data set of patients, we can have better results than a patient-specific method. And it's not surprising that we have like not the same efficiency as tailored PTX, because tailored PTX would be the best that we can have because it's what is used on the 6 patients of the dataset to compute the universal pulses. But it's pretty interesting, and we can see here on the images that the artifacts can be reduced, like the number of artifacts, that the images are more homogeneous. So yeah, that works really well. And it's a plug and play solution. So it's almost invisible for the user of the scanner, because you will just have to select the pulse that you want and the scanner will do the rest. And right now it's a really, really recent method, because it has first appeared in 2017, and it has only been performed in the brain and for some pulse sequences. So that's what brings me to the last point of my presentation, which is the project, my master thesis project. So what could be interesting to do is to tailor universal pulses for calibration-free B1 homogenization in the cervical spine, because it has never been done so far. And so that will present some obstacles, and the goals would be like to compare with the CP mode and the RF-shimming, as we just saw earlier, and to evaluate the benefits of the universal pulses for cervical spine imaging, because we are not sure that we could have the same results as in the brain, because these are 2 different regions, and we have some challenges to overcome. For example, the electromagnetic properties in the spinal cord are really heterogeneous across the tissues. The spinal cord is like located in the middle of the body, so we have to go to image it deeply. The proximity of the lung can also be a problem because of the breathing, and that can induce some artifacts. And the anatomy and position of different subjects can vary in this region because everybody is different, and so the anatomy differences can like make it harder to have designed pulse that will be efficient as it was in the brain, as we saw before. And so, yeah, accurate B0 and B1 maps are required to compute this. So it's important to select the good mapping techniques to overcome these difficulties. So what is important to remember about that presentation is that the B1 homogenization becomes really challenging when we are at 70 and more. The clinical use of parallel transmit is still limited by the SAR concerns. So right now it's only used at 3T. And a lot of methods are still being investigated in order to overcome these obstacles and to make it available clinically. So thank you, everybody.